In this video we're going to look at how iterative sequences can be used to find roots of the equation f of x equals 0. Now we know that roots of quadratic equations like ax squared plus bx plus c equals 0 can be found using the formula x equals minus b plus or minus the square root of b squared minus 4ac all divided by 2a. There are similar but much more complicated formulae which give the roots for cubic equations and quartic equations. In an amazing piece of mathematics, a young French mathematician, Évariste Galois, in the early 19th century proved that no such formula can exist to find the roots of quintic equations. So even an equation as simple as a polynomial equation of degree 5, there is no formula which is guaranteed to give us the roots of such equations, which means that we have to resort to some sort of numerical process to find the roots of such equations. In mathematics generally, and applied mathematics particularly, equations will often be met which are either impossible or very difficult to solve by formal algebraic methods. We must resort in such cases to using numerical methods, and in this video and the next two videos we will be investigating possible numerical methods for solving such equations. So let's consider for the rest of this video the equation x to the 5 minus 6x squared minus 73 equals 0. First of all, just define the function f of x as being x to the power 5 minus 6x squared minus 73. Well, we can see that f of 2 gives me minus 65 and f of 3 gives me 116. Given that that's the case, that certainly tells me that because I've got a polynomial which I know is continuous, we've got a sign change in a continuous function, so the equation f of x equals 0 certainly has a root in the interval 2 is less than or equal to x is less than or equal to 3. Now there are several different ways that one can progress to trying to get a more accurate value for this root. One very simple method is simply to keep dividing the interval into halves. So this is the process of interval bisection. So we take the midpoint of the present interval, call that m, we evaluate f of m and deduce a smaller interval containing the required root. And we keep repeating this process until the interval is sufficiently small to ensure that the answer is known to a required level of accuracy. So at the moment we know that f of x equals 0 has a root in the interval 2 to 3. So we take the midpoint of that interval, which is 2.5. We evaluate f of 2.5, which gives me minus 12.84. So I've got f of 2.5 is negative, but f of 3 is positive. So I now know the root is in the interval from 2.5 to 3. I now repeat the process again. I take the midpoint of the interval, which is 2.75. I'm going to evaluate f of 2.75, which gives me 38.9. So I now know that f of 2.5 is negative, but f of 2.75 is 38.9. So that tells me, because of the sign change in the continuous function, that the root must lie in the interval 2.5 to 2.75. So the next value I would use for the midpoint would be 2.625, and I could go on like this repeatedly, just decreasing or halving even the size of the interval. So interval bisection is a safe but fairly slow method of zooming in on the desired root. Another method is to set up an iterative sequence which, if it converges, will converge to a root of the equation f of x equals 0. So the first step we've got to do is we take our equation that we want to solve, and we must rewrite that equation in the format x equals g of x. So at the moment I've got the equation in the form x to the 5 minus 6x squared minus 73 equals 0. That can be rewritten as x to the 5 equals 6x squared plus 73, or equivalently x is the fifth root of 6x squared plus 73. And we then set up a sequence defined by the first term in the sequence is the midpoint of the interval containing the root, or in fact it can be any value inside that interval containing the root, doesn't matter, but the midpoint is a quick and easy one to use. And then the next term in the sequence is simply g of the previous term in the sequence. We're going to consider the iteration x1 equals 2.5 and xn plus 1 is 6 xn squared plus 73 all to the power 1/5. In other words, it's the fifth root of 6xn squared plus 73. Now, as we've seen in earlier work on sequences, we can use our calculators to generate these terms very efficiently. So the first thing we must do is put the value of x1 in and then press equals to put it into the answer memory. We must then go through and put the formula for our iteration in. So in this case it is the fifth root of 6 times my last answer squared plus 73. Press equals. That gives me x2, x3. Keeping pressing equals gives me all the subsequent terms in the sequence. And you can see that the sequence is in fact converging to a value which is somewhere around about 2.5727. Recalling what's happened on the calculator, we've got x2 was 2.56255, x3 was 2.57130, and so on. And by the time we got down to x6 and x7, they agreed to 5 decimal places. So this sequence is converging to a value which is approximately 2.5727. So it looks as if we've got a sequence here of values xn which converges to a value alpha, which is 2.5727, correct to 4 decimal places. If the iteration converges to a value alpha, then alpha is a root of the equation x equals g of x, and since the equation x equals g of x is equivalent to the equation f of x equals 0, then alpha is a root of the equation f of x equals 0. We can now use our sign change in a continuous function to verify that 2.5727 is indeed the solution of x to the 5 minus 6x squared minus 73 equals 0, correct to 4 decimal places. So to say that it is correct that 2.5727 is the solution correct to 4 decimal places is to say that the root lies in between 2.57265 and 2.57275. So if we use our calculator now to work out f of 2.57265, we get a negative number. If we work out f of 2.57275, we get a positive number. So sign change in a continuous function tells me that the root certainly lies in the interval 2.57265 through to 2.57275, and since all numbers in that interval round to 2.5727, we can say that the root is 2.5727, correct to 4 decimal places. So to summarise what we've done, we've said if the function f is continuous and the equation f of x equals 0 can be rewritten as x equals g of x, and the iteration xn plus 1 equals g of xn converges to a value alpha as n tends to infinity, then alpha is going to be a root of the equation x equals g of x, and because x equals g of x is simply a rewrite of the equation f of x equals 0, we can say that alpha is also going to be a root of the equation f of x equals 0. Now, as n tends to infinity, then we know that xn plus 1 tends to alpha, and xn also tends to alpha. But the fact that xn plus 1 is equal to g of xn means that as n tends to infinity, we've got g of xn tends to g of alpha, because g is a continuous function, and as n tends to infinity, the equation xn plus 1 equals g of xn becomes alpha, because as n tends to infinity, xn plus 1 gets closer and closer to alpha, and as n tends to infinity, g of xn tends to g of alpha. So we've got the equation xn plus 1 equals g of xn just becomes alpha equals g of alpha. So alpha is a root of the equation x equals g of x, or equivalently, alpha is a root of the equation f of x equals 0. Now we've already seen that the equation x to the 5 minus 6x squared minus 73 equals 0 can be rewritten as the equation x equals the fifth root of 6x squared plus 73. But there are lots of different ways in which we could rewrite the equation f of x equals 0 into an x equals g of x format. For instance, we could say that we've got x to the 5 is equal to 6x squared plus 73, and dividing each side by x to the 4, we've got x equals 6x squared plus 73 divided by x to the 4. Alternatively, we could say that we've got x to the 5 minus 6x squared equals 73, so x squared times by x cubed minus 6 is equal to 73, which means that we can write x equals 73 divided by x times by x cubed minus 6. Now what I'd like you to do at this stage is just pause the video and use your calculator to see whether or not the iterations x1 equals 2.5, xn plus 1 equals 6xn squared plus 73 over xn to the power 4, and the iteration x1 equals 2.5, xn plus 1 equals 73 divided by xn times by xn cubed minus 6, whether these iterations converge and will help us to find the root of f of x equals 0 or not. So pause your video, just work through that, and then start the video again. When we set up these iterations, the first iteration we set up was the one we've studied already, and we saw that that iteration converged to a value which was 2.5727, correct to 4 decimal places. However, you'll have found that each of the two iterations that we subsequently investigated don't converge, as we can see from the results that you got on the calculator and that I've obtained here from a spreadsheet. So this is telling us that we've got to be careful about the way in which we rearrange the equation f of x equals 0. And in the next video, we will find a graphical method of determining whether or not a rearrangement of f of x equals 0 into the x equals g of x format will lead us to a good iteration. So this concludes our first look at iteration methods to find roots of f of x equals naught.